Okay, it's time for my lecture. It's 8 o'clock already. Today we will start with the analysis of beam. I'm going to work on this example, and then we will come to the composite structure, and later we will talking about the frame. This is the end of week 11, and we still have the composite structure, the frame, and the task. So let me start what we have here. The beam that's shown on this picture has the support at A as the roller, at B as the pin, and at C as the roller. If you start by consider the beam, you will see that our beam is a kind of statically indeterminate beam, in which we have what? We have the unknown of 4, which is going to be A sub y, B sub x, and B sub y, and C sub y. So unknown is 4 is larger than the number of equation of equilibrium. So this one for sure is going to be degree of indeterminacy. And you may put the reaction onto this picture. So we see this is B sub y, this is going to be C sub y, and this is going to be A sub y. Since this is pin, you also gonna set this one as the B sub x. Okay, and after this we're going to select, okay, the redundant. This is statically indeterminate beam. We will set the B sub y as the redundant force. Okay, and if you set B sub y as the redundant force, then you're gonna use the principle of superposition. By using the principle of superposition, we are going to find one more condition, which is the compatibility condition to solve this problem. So by using the superposition, okay, we can consider the beam into 2 cases. Okay, so if you select this, we're going to start by the beam that we consider over here. It's going to have what? It's going to have the roller here, the roller here. Okay, and as you can see, this is going to be the B sub y, but anyway, when you change this B sub y to be correct, the B sub x still there, so we have the roller, okay, in accordance with this B sub x, and the beam subjected to the uniformly distributed load of 25 kilonewton per meter. This is going to separate into 2 beams. One is going to be the high Mary beam, okay, subjected to the load, and another one is going to be the beam that subjected to the B sub y. So by doing here, okay, our beam will be this one, going to be the same, the roller, and this one you still have the roller also. But the problem over here, the primary beam is subjected to the 25 kilonewton per meter. But for this one, okay, is going to subjected to the B sub y. Okay, this is the first one that we have. And then by doing this, the second step, okay, we will write down the compatibility condition, That is the condition that's taking care of the degree of indeterminacy. And then by consider B sub y as the redundant. So what we have is we're going to consider at B, okay, and then we got to draw the elastic curve. So we draw the elastic curve of the beams. Okay, we start by taking care of this one, and you can see under the application of this force is subjected to uniformly distributed load. So you can draw this elastic curve easily. It's going to be what? Symmetry. Okay, under this force. And then what we have is the deflection over here due to 25 kilonewton. We call this as delta sub B or V sub By. Okay, and also this one is what? This one is subjected to the force. Since the structure is not in symmetry, this is 10 meter, this is 20 meter. I didn't draw it quite on scale. Okay, and then what we have is what? This one will have non-symmetry. This is non-symmetry. This is symmetry. But we are going to have the deflection over here. Okay, since B sub y is unknown, usually we determine the deflection here by setting B sub y equal to 1. And then we set this one to be the deflection of small f, at what? At point here, at point B, when the force applied at B, and the total force is B sub y just times B sub y with kit. Okay, and then we have this type of elastic curve. And then when you consider the deformation or consider the elastic curve, we consider the elastic curve. Okay, Ajahn, should we consider this one? You can consider this one if you like to consider it, but it's maybe just enough. This one may be defect, something going to be very small thing like this, and it's supposed to have the inflection point over here. It's just a guess, okay? And what we have is at point B, what we have is the deflection here is going to be 0. So we have the deflection here equal to 0. And then this is equal to the deflection here is going to be the delta B. If we set downward is positive, so this one is going to be negative minus f sub b sub y, and what we have is the compatibility condition, okay, in which we are going to determine the b sub y. Okay, our b sub y will equal to the delta sub b, and then divided by f sub bb, and then you will get this equation, and based upon this equation we got to find the force deflection. This one is a deflection or displacement, okay, relationship. if we talking about this, in this problem, we didn't have the deflection table, okay? And most of the time, I will give you the way to determine this deflection. You may determine this deflection by using the virtual work, okay? Or you may find it by using the conjugate beam, and you may find it by using the method of superposition, okay, method that you have it in mechanics of material, okay. This will going to use the deflection table. Anyway, on this one we didn't have that, so let me try to use the virtual work, okay, to solve this problem. Why I can use virtual work? Because the loading is uniformly distributed load. If you use the conjugate beam, you may have some problem with the determining of the area of this structure, okay. Okay, basis upon that, this is going to be 10 meter, this is going to be 20 meter. We are going to separate this beam into two portions, okay. We're going to separate this beam into two portions. So basis upon this, what we have is we are going to have the beam that's subjected to the uniform load. So we start by phi delta B by using this virtual work. So let me determine this. Under the application of this force, we have the force of 25 kilonewton per meter. Under this force, we will have this one and this one. And since the beam is in symmetry, the total length is 30. So half of this force will be here. So this is going to be 25 and then times 15 meter. Okay, it's going to be 375 kilonewton. And the same is going to be here due to the symmetry. This is going to be 375 kilonewton. So this way, I'm going to review you how to determine the deflection. Okay, and then the beam gonna deflect something like this, and we're going to determine the deflection at the point, at this point of x. This one is going to equal to 10 meter, okay. And then what we're going to do is we're going to cut this beam, okay. Basis upon the principle of virtual work, we're going to determine the moment, okay. So by using the virtual work method, virtual work method, we have what? We have to what? To put one unit force over here. So this 1.0 unit force must have with this one of delta sub B. So we have this one of delta sub B. It's going to be the integration. So you got to do another one of this, and it's going to subject it to the 1.0 force, and this 1.0 force times this virtual 1.0 force times with delta sub B. This one is going to be the external virtual work, which is going to be equal to the integration of what? Of the moment, okay, of what? Due to the force. So under the 1.0 unit load, we are going to have what? We are going to have the moment. the moment here is going to be small m. The moment here is going to be capital M. This moment capital M cause the deflection of this beam, and the deflection, the change over here change with the position of x. Okay, so we have this one as the internal virtual because this one is going to be the moment due to the virtual 1.0 unit load, and it's going to have the change of this one is going to be d theta, and then this is going to be equal to the integration of what? Integration of small m by using the elastic beam theory. Okay, we have the change, the curvature over here as what? As d square v by dx square equal to m over ei. And then we can draw this equation again as dv by dx, okay, equal to m over ei. And this equation is the theta. So the d theta is going to be m over ei dx. So it's going to be m over ei dx. Now we're going to determine the moment m over here. Okay, and also m supposed to determine over here also, because this is going to be the path of from point A to point B, and this part is from point C to point B. They are different, so call this as the M1. Okay, and call this is small m1. Call this is the M2, and call this one as the capital M2. The direction of the moment supposed to based on the sign convention that we have in the mechanics of material. Okay, and based upon this, we're going to determine the capital M. Okay, and then we have this one as the X1, and we have this one as the X2. The load here is 375 kilonewton. 375 kilonewton. Okay, if you do the summation of the moment equal to 0, you will get M2 equal to 375, and then that's gonna have what? That's gonna have X2. Okay, and this one also you will have this one summation of the moment equal to 0. This is 375 times X1. Okay, X1 going to be integration from this one to this one. This is going to be integration for 10 meters, but for this one we're going to integrate it from C to B. From C to B, that is going to integrate for 20 meters. They are different. Okay, and then we come to determine this under the application of 1.0, and then this is going to be 10 meters. This is going to be 20 meters. You do the summation of the moment about A equal to 0. So the B sub y here gonna come for 30 meters. Okay, and then it's going to be equal to this one times 10, 1, and then times 10. The B sub y is going to be 10 over 30, 1/3. So this is going to be 1/3. And then you do the summation of f sub y equal to 0. Summation of f sub y equal to 0. Our a sub y here, a sub y plus 1/3 is going to be 1, and then the a sub y going to be 2/3. So this is going to be 2/3, and then what we have is going to be this is 2/3, and then you summation of the moment equal to 0. Your m1 is going to be this 2/3 times x1 is going to be 2x1 divided by 3. Okay, and then also you will have this one as the x2, and this is going to be 1/3. So if you do the summation of the moment equal to 0, your M2 is going to be x2 over 3. Now you have everything, right? You just put it back into this equation. So you have this one as 1.0 times what? Times delta sub b. And this is going to be the integration of this from a to b. Integration from 0 to 10. So we have the first integration. Let's see. This is wrong. We find this one. Okay. This one, the same thing. From 0 to 10. And then what we have is we're going to do the integration, okay, to this portion of 10 meters. So this is going to be 375x1, this one. And then time 2x1 over 3. And then that is going to be what? dx1. That is going to be dx1 over EI. And then we got to the integration from C to B. Okay, we're going to do the integration from 0 to 20. And then this is going to be 375 x2. And then it's going to time this one, time x2 over 3. So you do the integration dx2 over EI. Okay. By the final calculation of this, you will get the delta sub b equal to 145,833.33, okay, over EI. Just do the integration over EI. So you're supposed to integration of this, and then since I make this thing correct? No, this is not correct. This is not correct. I'm supposed to put one over here downward. Okay, one over here supposed to be downward. So in order this one to be correct, sorry for that. So this one, you will get this one as the positive. If this one is positive, this one gonna be downward. Okay, this one going to be downward. That is the wrong direction. Let us make it correct. Okay, over here. And then you got to determine the second one is the F sub BB. Okay, again, to determine F sub BB, we got to put the 1.0 into this position, and then that's 1.0 is going to be produce this one of F sub BB, this one for F sub BB, and then it's going to be equal to the integration of what? Of moment. Okay, since the picture here when we sub y equal to 1 is going to be just in the opposite direction of this one. So what we have is going to have this one as the minus m. Okay, and then we have the force that's due to this m also. So this capital M going to change to minus m. Okay, and then we have this one for dx over EI. What I mean is, based upon this one, we can use this one to determine the small m and the capital M, because the picture going to be the same. Okay, so this is going to be equal to the integration of m square dx over EI. Okay, and by doing this, we will get F sub BB equal to the first integration. You do the integration from 0 to 10. Okay, and if the force is down here, the F sub BB will be like this. So this is going to be F sub BB times 1. Okay, and then the 1.0 F sub BB will be integration of this one 0 to 10, and then it's going to be 2x1 over t squared, and then this one is dx1 over ei, and then plus this second part is going to be m2, the integration of 0 to 20, and this one is going to be x2 over 3 squared. Okay, this one is going to be x2 over 3 squared dx2 over ei. Okay, and then after do the integration, you get this one of 26.3 divided by ei. Okay, and then this one is going to be meter squared. Okay, it's going to force times this one squared, but this one it have 1 unit. Okay, so just left it, and this is going to be what bases upon this. This is going to be downward. Okay, downward in the same direction as the 1.0, and then what the value of this one? Don't worry, this is going to be equal to this one. No matter the force 1 unit is upward or downward, it's going to be the same magnitude of this. So next, step number 4. Okay, we solve for b sub y. So our b sub y 1 is going to be this value. Is going to be 1, 1, 4, 5, and 8, 3.33, and then divide this one by this one. Okay, it's going to be divided by ei, and then this portion is going to be 296.3, and then the ei here just move up. Over here, just cut and cut. So you get this b sub y to be 492.2 kilonewton. So what we have is the force that occur here to be 492.2 kilonewton, and then we're going to what? To go to the step. The next step is going to be 1, 2, 3, 4, and 5. In step 5, we analyze the beam. We analyze the beam for reactions, and we analyze the beam for shear diagram, for moment diagram, for elastic curve. Okay, and for what? For the reinforcement pattern. Reinforcement pattern. We will use the result. Okay, to find a lot of things. The reinforcement pattern gonna put here. If the beam is the RC beam, is the reinforced concrete beam. Okay, and basis upon this, just start over here. We just do the summation of the moment at A equal to 0. If you prefer summation of x sub x equal to 0, we will have b sub x equal to 0. If you take the moment here, c sub y gonna rotate in the counterclockwise direction. So we will have c sub y. It's gonna have 30 meters. That is going to be 30 meters. And then this one is what? This one is this way, right? And then plus 492.2, and it's going to time 10 meters. Okay, and then that is going to be equal to this force. This is going to be what? This is going to be 25. Okay, time what? Time 30, and then is going to be half of this is going to time 30 divided by 2. Okay, by compute this, you will get C sub y to be 210.9 kilonewton. C sub y is 210.9 kilonewton. Okay, and then you do the summation of f sub y equal to 0. Actually, you're supposed to do at the bottom, but I don't have area to show you, so it's going to be clearer to do it over here. Upward is positive, so the a sub y is going to plus 492.2 plus 210.9, and this is going to be the value of this is going to be 25 times 30. Okay, and then you're supposed to get a sub y equal to 46.9 kilonewton. This is 46.9 kilonewton. Okay, and then a little bit further, we come to draw the elastic curve. Let me put this one as the x meter. This is 0, this is 10, this is 20. We have this one of what? Of 4.9. So this one going to be very small. This one is 492. That is going to be large. Okay, if we put 100 kilonewton per 100 kilonewton per 10 millimeter. This is going to take about 5 centimeter. 1, 2, 3, 4, 5. It won't work. Okay, just put it to be the scale of 200 kilonewton per 10 millimeter, and set this one as the vertical line of V kilonewton. So this is going to be very small, right? Yeah. Okay, this is going to take about 2 millimeter something. This is going to be up like this. This is going to 46.9. Okay, and then we have the dv by dx equal to minus 25. I believe it's going to be downward like this. So what is the shear over here? It's going to be what? The shear over here, minus 46.9, and then it's going to be minus of this area. This is going to be 25 times 10. Okay, so UV is going to be minus 250 plus 46.9, and this is supposed to be minus 203.1 kilonewton. So basis on this 203.1 is going to be about, okay, this one 10 millimeter minus 203.1. So we get this as the shear diagram, and this is going to be 0, and you may put this one for minus 25, minus 25, and minus 25, just show the slope. Okay, and what this one? Okay, if you are good at this, now you're supposed to know this is going to be 46.9 divided by 25, and when you divide this one, you will get it for what? 46.9 divided by 25. It's going to be 1.876. Okay, it's going to be 1.876, or may say 1.88. 1.876 meter. Let's see, if you prefer just 3 significant figure, it's going to be 1.8. So it's going to be 1.876 meter. And then what we have is this one is going to be subjected for 92. So this is going to be up. Okay, about this one, about nearly 2.5 centimeter. This is going to be up, okay, over here. And this is going to be plus 492.2, and then minus 202.1. So this is going to be 289.1. Okay, and then we have the slope here again. The dv by dx gonna be minus 25. And we know this force is going to be 210.9. This force 210.9 is going to be upward force. Okay, to close this is going to be minus 210.9. Ajahn know that because this is going to be move up. Okay, like this one is 49.9. But this one will start by the negative to cause it at 0. So this one is going to be the curve like this. Okay, and this is going to be the slope. It's going to be the slope of minus 25. Okay, and this is going to be the shear diagram of this picture. You also can determine this length by this one is going to be 289.1. The height here divided by 25. Okay, you may get this one for 11.56 meter if you just consider 2 digits here. Now we move to determine the elastic curve. Oh no, sorry, the moment diagram first before the elastic curve. The moment here is 0. The moment here is 0. So we have the moment at the end of the beam is 0. This is going to be x. Okay, this is going to be 30, 10, and 0. And this is going to be the moment diagram, right? So it's going to be moment in kilonewton meter. And then we determine this is what? Start from here. We have 46.9. So the slope here, the dm by dx is going to be 46.9. And somehow about here, the dm by dx is going to be 0. And the moment here minus this one minus 0. And it's going to be equal to this area, 1/2 of 1.8. Sorry, 1/2 of 1.876. And then times 46.9. Okay, if you push it together, the m here supposed to be about 44 point something. It's going to be 46.9, and then time 1.876. Okay, this is about 43.992. Okay, let's say this is going to be 43.992, and it's going to be very small. Okay, just put the scale of 200 kilonewton meter per 10 millimeter. If this is 42, it's going to be very small here. Okay, if you prefer 43.99 kilonewton, and then you may put this one as the curve, and the slope here is 0. If you are more detailed on this, okay, you may put this one as the mark to show your slope, to express your understanding of what you do. Okay, and then what is going to be the moment here? We got to consider it. Okay, so what the distance we have here is 1 minus 1.876. So this is going to be 8.124 meter. Okay, and this is 289.1, this one, and divided by 25, this is 11.56 and 4. Okay, and then what we have is next, the moment here we don't know yet. Okay, we just take the moment in this point minus this one 43.99, and then that is going to be equal to the area over here. That is going to be minus of 1/2 of 8.124, and then time 203.1, 203.1. Okay, if you do the calculation of this, the answer going to be like 781. The M is going to be 203.1 times 0.5 times 8.124. Okay, and then 824.99 minus 43.99. You're going to get this one for 781.0. This one 781.0 kilonewton meter. And based on this is going to be about, wow, this is going to be about 200, 400, 600, and 700. This is going to be a little bit large scale. It's okay, just put this one 200, 400, 600, 700, and 781. Okay, it's supposed to be somewhere over here, and the slope here, and the slope here. Oh, sorry, what happened? I lost. I put something over here. Okay, let's move. Okay, and then the slope over here is going to be what? It's going to be minus 103.1. So the dm by dx is going to be minus 203.1, and this is going to be the slope at this point, and the value of here is this one, and the curve will going to be something like this. Okay, and then we go a little bit further in the other way of this one. The shear change to 289.1. So coming into this way, the slope here, dm by dx is going to be 289.1. And then it's going to come to be over here. The slope over here going to be 0. The moment at this location, 11.564, is going to be minus of what? Minus of this value. Minus of this is minus 781.0. Okay, minus of the minus 781.0 equal to the area over here, equal to 1/2 of 11.564. Okay, and then times 289.1. And then if you put it into calculator, you're supposed to get this one about 890 kilonewton meter. Okay, that is going to be 4.5. 4.5 is going to be the curve like this. Okay, this is going to be the curve like this, and then the dm by dx gonna be 0, and then the curve going to be something like this one. Okay, and again, this is going to be your dm by dx. So this is going to be the slope of this, and this is going to be the slope over here. And for sure, the last one you can draw the picture easily, because from this one is going to be downward. Here the dm by dx gonna equal to v here minus 210.9, and the curve is going to be something like this. Okay, this we draw it based on the scale, and then we have this one for positive. We have this one for negative. We have this one for positive. We have this one for the point of 0 moment. Okay, this one for the 0 moment. If we draw the elastic curve over here, okay, you got to project this point into the beam also. Okay, and then after you project this one to the beam, you will get this one as the concave concave upward. Okay, this part of this structure supposed to be concave upward, and this one is going to concave downward until here, concave downward. Okay, and then at this point it's going to be a smooth point, and this is going to be the concave what upward. This is going to be the big elastic curve over here. Okay, this is for sure going to be the thing that we prefer to, and then this is going to be the zeta sub A, and this is going to be the zeta sub C, and again this is going to be the zeta sub B. This is going to be zeta sub B. This is going to be the inflection point. Okay, this is going to be the inflection point. So that's we have for the elastic curve, and then we got to put this one into this reinforcement. Okay, if the beam is the RC beam, let me put this one, okay, downward over here. We will use the moment diagram to put the reinforcement into this beam. If this beam is a what? Is a reinforced beam. Just put this one over here, okay? And what we have here is what? This is going to be the point that we put the reinforcement. Anyway, just let me put all the reinforcement. Usually we supposed to run all the reinforcement along the beam. That is for the stirrup, also for our ease of construction. And this is concave upward. So the beam must be reinforced more over here. The beam must be reinforced more over here. And then this is concave what? This is concave upward. Okay, so this portion going to have the reinforcement, extra reinforcement like this. And this portion we will put the extra reinforcement like this. Okay, so this is going to be the pattern that we will put the reinforcement over our structure. And then we also need to consider the shear force, and then you can see the shear force distribute unequal, and large shear force is this in this area. So most of the time, if you prefer, you're supposed to separate the reinforcement of this beam into this portion and this portion, and the stirrup on this way and this way is supposed to be the same. It's going to be more stirrup, okay, in this area. This area must put more stirrup. Okay, the spacing between stirrup gonna be very close. Yeah, okay, and since the portion here has a small shear, you may put it in the double spacing compared to the previous one. Okay, this is a kind of reinforcement of this one. And for this portion, yes, you're supposed to put in the same distribution. Okay, same distribution as this one. Okay, the distance. And then the left of this, just put this one in this one. This kind of pattern will be appropriate. Okay, you can save some material for putting appropriate spacing of the shear stirrup. And I will discuss this with you again when you take the capstone design. And many times Ajahn Anop, Ajahn Mongkol also will check your knowledge later. Okay, this is the end of analysis of statically indeterminate beam. Okay. Okay, and I show you both by determine the deflection basis on the manual computation, and from the previous video basis on the deflection table. Okay. Okay, next we come to the composite structure. Okay, this structure is different from the beam that we discussed from the previous lecture. Usually we just support this portion by the roller. Okay, if we support this one by the roller, what we have is the point B won't move. But for somehow, if you hang this beam by using the rod, okay, by using this rod, the BC rod, you can see this kind of structure at the civil engineering building at Concan University. Okay, there is a lot that hang the cantilever beam, something like this. Okay, this we call this beam as the composite. Okay, composite beam structure. Composite structure is going to the combination of the beam and the rod. Okay, and then I'm going to say again, due to this is the rod. Okay, the rod can be deformed. Okay, when the rod is deformed under the application of the applied force, it's going to be different from the roller. Okay, if it's supported by the roller have no deformation. So the compatibility, okay, the compatibility must be taking this kind of deformation into the compatibility, must consider this thing into the consideration. Okay, we have I have the PowerPoint and video clips, okay, on this beam, this composite structure over here. Okay, again, this is a specific thing. This is a composite structure, and this composed of at least 2 types of structural member. Okay, for this one we have the rod. Okay, the rod is a kind of axial load member. The rod is called the 2-force member. This rod will subjected to what? To compression or tension only. Okay, only. And it's combined with what? Combined with the beam. Okay, for example, this one, this structural member is considered as the beam. Okay, this rod, the rod BD usually is connected by the pin here and by the pin here. If the structure, the composite structure is in the form like this picture, this composite structure is statically determined. Because of what? This is going to be the 2-force member. So under the application of the force, you may imagine this structure will move, okay, in the form like this. And then this is going to be what? This is going to be in tension, okay, for sure. And this is going to be the force of F sub BD. And then due to this, we will have this one of A sub X, okay, and we will have this one of A sub Y. So you just summation of the moment about A equal to 0, you can find F sub BD. I like you guys to work by yourself. And then you can determine this A sub y by summation of F sub y equal to 0. You will find the A sub y, and later if you do the summation of x sub x equal to 0, you will find the A sub x. Okay, this one is statically determinate if you draw the free body diagram of this. And we also have this one in the form of statically indeterminate, which is the same as the one that I show you in the previous picture. Okay, and the load that applied to structure may be, let's say, W equal to 10 kilonewton per meter, and this is maybe 4 meter, and just put this one to be 2 meter if the structure has the stiffness of EI and the lot have the stiffness of AE. Okay, we can use this information to analyze this structure. Okay, and I like to show you this guy, and then for the statically determinate structure, you have analyzed this structure already since the engineering static. Okay, I left this one for your assignment, just practice. And for the second one, just come to what I have in this extra example. Let's move this one to, okay, this one. Okay. Okay, when we come to here, let's us consider the beam again. The first step, you consider, no, not the beam, consider the composite structure. Consider the composite structure, and you can see this composite structure combine the beam with the lot under the application of the force, the point B, okay, and the 40 kilonewton, okay, the point B is the deformate, okay, to V sub B double half. And then again, we just come to the same consideration. By consider this, we will have this one of A sub y, this one for the A sub x, this one from the M sub A, and for sure, okay, this one we will have F sub BC. Okay, so we have what? We have unknown equal to 4, larger than the number of equation of equilibrium, which is 3. So the structure have degree of indeterminacy C equal to 1. Okay, and then you will let this one. This is a lot more complicated because this point have two forces and one moment. It's going to be better to just set F sub BC as the redundant force. That is going to be easier. And then we also can use this thing, okay, to determine the deflection later. Or if they won't give us this detail, we can use the conjugate beam, the virtual, okay, to determine it. Okay, and then next we're going to use the principle by using the principle of superposition. Okay, if we use the principle of superposition, this beam will separate into 2 more beams. Okay, by using this, okay, let's consider the beam here. The beam here is going to be equal to the primary structure, and it's going to plus with the structure over here. Okay, we have this one, we have this one, and let's say we have F sub BC as the redundant force. So the support at B still be fixed support, and then under this 40 kilonewton, this one will subjected to the force of F sub BC. Okay, and then let's say we have okay the beams as shown, and then we got to draw the elastic curve. Second we find the compatibility condition at what? At B. Okay, at B. And what different? We got to draft the elastic curve. Okay, and then what we have is this structure is going to fix here, and since there is no forces over here, the deflection on this portion is curved, but the deflection on this portion is going to be linear. Okay, it's going to be linear, and this is going to curve. Why this is linear? Since this portion have no forces. Okay, and I said, let's say this one is going to produce at point of B V sub by. Okay, it will be sub by. And then under the application of this force, we know it's very quick. This one will have the deformation, something like this. Okay, and this is going to be what? This is going to be V sub B palm. Okay, let's call this V sub B. Just call them V sub B. Okay, and this is going to be V sub B palm. And what we have here is going to consider the elastic curve. This one going to be V sub B double palm. If we set downward is positive, that is going to be equal to what? V sub B here. V sub B here. And then over here, we're going to have this one for minus V sub B palm. The problem is we're going to determine, okay, everything over here, and you can see this one. We may use this picture to determine it. So V sub B palm, we may use this one. Now our X, okay, this time we put the position of X equal to 4 meters, or it's going to be the L. And also under this movement, okay, the lot. If you prefer, this one also has the free body diagram. The lot here is going to subjected to the force of F sub BC and F sub BC. The lot is what? The lot is going to be the two force member, and this lot is going to be in tension. Okay, it's going to be two force member. It's going to be in tension. So what happened is, under the force, the lot subjected to F sub BB, and the lot will elongate, okay, by this amount of V sub B palm. Okay, so we will find the V sub B palm based on the deformation of the lot. Okay, and then we will find the V sub B basis on this and V sub B palm basis on this. So the third step, we the this time we call force displacement relationship. This one will be the force and displacement, not the deflection. Okay, for the lot here V sub B palm, and then we know this one is going to be sigma equal to E times 10, and F sub BC divided by A equal to E of what? E of what? E of delta. This is going to be V sub B palm divided by L. So V sub B palm will be F sub BC, times what? Times the L divided by EA. So this is going to be F sub BC times L divided by EA. And what we have is going to be the lot has the diameter of 12, okay, millimeter. This is diameter. So the A is going to be pi d square over 4. Okay, this is going to be the area of the lot. So put everything together. So we will have this one for F sub BC. And the lot is 3 meter times 3.0 meter. And then divided by, we got to change the E. Okay, the E of 200 gigapascal is going to be the 210 power 6 kilonewton per square meter. This one is 210 power 9 Newton per square meter. Just change it into this. And the area is going to be pi. Let's say, just put this one, pi, and 12 millimeter, 0.012 square, okay, divided by 4. Okay, divided by 4. You may use just pi r square. Pi r square going to be easier. Okay, just may use this one for pi and 0.006 square. Okay, this is going to be in the unit of meter square. When you put this one together, you will get this one equal to, 1.26, 10 minus 4 F sub BC, and this one gonna go downward. Okay, this is the first one of F sub BC. And for the V sub B, okay, next for the V sub B. V sub B come from this equation, and what we are looking for is the deflection over here. So deflection over here come from this equation, because this equation used in this portion. Okay, so this is going to be equal to, don't worry about this one is downward, this one PL square over 24 EI, and this X is L, so just put this one to be 3L minus L over 2, again PL minus L over 2 is going to be 6L minus L over 2 is going to be 5L over 2. So this is going to be PL power 3, 5 divided by 2. 2 times 24 is 48 EI. That is going to be 5 PL cubed over 48 EI. Okay, and then you put it, it's going to be 5 times P. P is going to be 40 kilonewton. And then the L is going to be 4 meter. Just put this one 4 meter and then divided by 48 EI. You use a proper unit. Okay, and it's going to be E, 210 power 6 kilonewton per square meter. And the I is here. 186 10 power 6 millimeter power 4. That is going to be 186 10 minus 6, okay, meter power 4. And then you put everything together. This is going to be 6.83 10 power 3 meter, and it's going to get downward. Okay, it's going to get downward, and this is going to be 6.83 millimeter, and it's going to be downward. Okay, and please check this one. I suppose this one to be in the unit of millimeter also. Okay, and then the last one. The last one is V sub B prime. It's V sub B prime, and then we come to this one. Okay, this one is what? This one is going to be x equal to PL square over 6 EI. And then this is going to be L minus L. This is 2L. This is going to be L cubed over 3 EI. Okay, and then over here is going to be PL cubed over 3 EI. And then what we have is what? This is going to be F sub BC. It's going to be force here. Okay, F sub BC. And then the L is going to be the L of the beam is going to be 4.0 meter. And then it's going to be what? Going to be divided by 3 EI. And then this one going to divided by 3 EI. 3. And then E. And then I. Okay, I is the same over here. Okay, 186. And then 10 minus 6 meter power 4. Cut. Okay, and this one is going to be 4,000 if you're gonna put it into millimeter. Okay, this is going to be 4,000 divided by 600. 4,000 divided by 600 divided by 186. That is going to be very small. Okay, and this is going to be 0.0358. If you put this one, it's going to be 1, 2, 3. This is going to be 4, right? Yeah, 4 meter. F sub BC times 4 meter, and then divided by 3 EI. Okay, let me put this again. This one 4,000 millimeter, and divided by 600. Okay, and then divided by I equal to 186. Okay, that is going to be 0.03584 millimeter. Okay, this one is the EA. Okay, you got to do the computation to make sure everything correct. 160 times 5 divided by 200 divided by 186. That is going to be very small. That's wrong. 160 times 5, okay, divided by 200. That is going to be 4, and then divided by 186. Okay, it's not correct. Oh, forget about 48 here. 48, okay, divided by 48. Okay. The number is not correct. Let you guys check about this. It's going to be 5 times 40 times 4. Okay, that is going to be 1048 EI divided by 48 divided by 200 divided by 186. Huh, why? How come I get this one for 5.6? So I like you guys to check about this. This is not quite correct. Oh, it said 1210. Okay, anyway, just put the E. Let's see. 40 times 4 times 5 divided by 48 divided by 186 divided by 2 and 10. No, not correct. Okay, I like you guys to check this number. And then when you put this number back, you will get the F sub BC. Okay, you will get F sub BC by doing this computation. Okay, and then after this one, the number 4. Okay, so for F sub BC, when you get F sub BC, when we see over here, you can determine the reaction A sub X, A sub Y, M sub A. And then later you may draw the shear diagram and the moment diagram. Okay, I'm not quite sure what happened. This is not correct. The solution here is going to be 40 times 4. That is correct already, right? That is going to be correct. This is going to be the deflection V sub B here. 5 times 4 times 40. That is going to be 800 divided by 48. Okay, divided by 186. Okay, and if we divide it by 200, it's supposed to be about 4.4. 4.123. Okay, let you guys check this one and put this one. You get F sub BC again. You will get the solution of this. I don't have time to fix this. Sorry on that. I will go back and check this one again. I don't know how come. I think it's correct since it's come from the textbook. Okay, divided by 186. Yes, this is not correct with that. This is going to be times F sub BC. Okay. Anyway, okay. Let me finish this one, and we still have more example on this in the video clip, but I won't put this into the examination. Okay, we will focus on the beam, we will focus on the frame, we will focus on the truss. Okay, and let me pass this. Okay, the composite structure won't be in our final examination. I'd like you guys to know about it. We come to the frame. Okay, analyze the frame is going to be something that's important to you because it's require you to know both chapter 7 and both chapter 6. Okay, and then they said this is a rigid frame, so the beam is going to be the rigid connection. This is going to be the rigid joint or rigid connection. And then the A is going to be the fixed, okay, and the C is going to be the roller. So let me first we consider the frame. Okay, when we consider the frame as here, since this one is the roller, for sure we will have the C sub Y here, we will have the A sub Y here, we will have the A sub X here. I like to put one more force over here to produce the A sub X, and also we have this one for M sub A. Okay, and let me change the load over here from 75 kilonewton to be 7.5 kilonewton, and then the beam have the same EI. So this is going to be the EI, this is going to be the EI. Okay, A is fixed, C is the roller, B is the rigid joint, using the consistent deformation. And then they ask us to use the copper redundant force. Okay, when we consider the beam, we will have the unknown equal to 4, which is larger than the number of equation of equilibrium equal to 3. So this structure has degree of indeterminacy equal to 1. And then if you like to select again, the principle is using the force like this. Okay, that is going to not involve with a lot of things over here. If you use the C sub y, it's going to be easier when you use the A sub y or the M sub A. Okay, by doing this, actually we just let the C sub y as the redundant force. Just use this one as the redundant force. And then what we have is we're going to use the principle of superposition and consider the deformation of this structure. For sure, this one will separate into two more structures. So by using the principle of superposition, again, we draw this superposition. We have to separate this frame into two more frames. This is 3 meters, right? So just put this one up, okay, and then plus another one here. Okay, just you put to a smaller scale over there. Just put this one and put this one, and then it's going to plus, and this is going to be the primary frame. This one is going to be the primary frame. Okay, we just put this C, okay, this C as the redundant force. So the A is still the same thing. The A is still the same thing. This one subjected to the given force of 7.5 kilonewton per meter, and also have this one for 13.5 kilonewton. But for this one, we're going to put the C sub y here, and then you can see the combination of these two pictures is going to be with this one. And then next, we just set the compatibility condition at what? At point C, compatibility condition at C. And then by doing this, you got to draw the elastic curve. And this one is what? This one is the roller. Since this one is the roller, for sure, under the application of the force, the roller can move, okay, in what? In this direction, then this direction, and then this is can cause it for what? For the delta of what? Of delta for Cx. Okay, this is for the delta for Cx. And the frame cannot the frame cannot move. Okay, and if we cut this portion of the frame, if we cut this portion of the frame, and you imagine it, okay, you can see this structure will subject it to only the C sub y, and it will has the shear, the axial force, and the moment here. okay, and for sure this one, the moment here supposed to be 0. So if I imagine it, okay, this portion of the beam supposed to be in the straight line, okay, and this beam won't move in the x direction. The delta for bx equal to delta for by is going to be 0 because of what? Because there is no axial deformation of the beam and column of the frame. We don't have it. So the B is going to be there. And under the application of the force, this is fixed. And this must keep the light angle. So this one gonna be in this direction, and the angle here will keep like this. So what I imagine, this one will go down and then is going to go up. So this portion will have concave downward, concave upward. Okay, this one supposed to concave upward like this, and there is the inflection point here. You may just write it IP. That's from the inflection point equal to inflection point. Okay, and then by doing this, next what we have, we're going to do the same as the analysis of the beam. What we do is going to consider what? The delta sub Cx. Delta sub Cx is 0. So by doing this, you may set this one. This is going to be 0 equal to, okay, coming to this one. By doing this one, this is fixed, okay, and this is what? This is free. The structure over here going to be subjected to the force like this. So it's going to curve like this. So I believe this portion is supposed to have the same thing as what I show you from the protector. Okay, this is going to be like this. And the angle here must keep in the light angle. So this is going to be the deformation of the frame. Okay, our point C will move here, and what we have, this one will have the deformation from here, and it also has the rotation over here. But we consider this. This is going to be what? This is going to be delta at what? At C. Okay, we may put this one as V sub Cy if you prefer. And then this is what? This is downward. Okay, we have the delta sub C. We put downward is the positive. And then coming into this. By doing this, you're going to push this frame. Okay, push passing to this column. And then the frame is supposed to deform like this. So I believe under the application of this, okay, this one, as I show, is going to have this kind of deformation. And then by doing this, the angle here must kept into the light angle. The light angle, okay, it's a fixed in the fixed connection, or it's a fixed joint. And then again, the deformation of this can be considered to be in this way, and also if you connect this one and connect to this one, this is going to be the slope. And what we consider is going to be the vertical direction, because we use the C supply as the redundant. This is going to be F at what? At point C. Due to applied force at point C, and then it's gonna have the force of C sub y, and this is upward. Okay, so it's going to be minus of what? Minus of f sub cc and time c sub y, and the c sub y gonna be equal to delta sub c divided by f sub cc is going to be our equation. Okay, we have this one as a compatibility condition at point C, and by considering the elastic curve, of the frame, you got to put this one word to show how this equation come. And now we got to work on the big problem. You got to determine the force displacement relationship. So the third, we got to find the force displacement relationship. What we're going to determine is going to be delta sub c and f sub cc. We only have one method to do this by using the virtual work method. We have only one method to solve the frame. For the other method, I will left you for your study. By doing this, by using the virtual work method, we are going to get what we have. What to put 1.0 force, 1.0 force, and time the delta sub c. And then if we time this, it's going to be equal to the integration of small m capital M dx over ei, and then the big M will come from this kind of picture. This kind of picture. Is subjected to this one, and what we have is the 1.0 unit load. Let's see. Not this one. Just put this one. And what we have is going to be the delta sub c. The delta sub c will time with the 1.0, and then the 1.0 is going to be in this direction. Just may put this one into this direction at point C, and you can see the C sub y and the 1 point unit very close relationship, except the C sub y is upward. And we think the 1.0 maybe upward or downward is just only for your consideration. Let's see, and we put this one to be 1.0 at C sub y. And if you use this one to determine M, and then you use this one to determine capital M, and then you will see the direction of this going to be in opposite. And if you put this one into this equation, you will get the negative. So don't worry. But when you determine f sub cc, it's going to be easier to do so. And then we're going to analyze the structure. And let me put this one over here to make things a little bit more clearer. Just put this frame, and we're gonna set the coordinate. Let me put the coordinate like this to be the x2, and this one to be the x1. Ajahn, why don't you put from the reference point A, not for this one. If you use the point A and the origin, you got to determine the reaction. So by putting in this direction is going to be much more convenient. Okay, and then by putting like this and under the application of the force, let me cut this one over here. We will get this portion of the frame with reference to the coordinate x1, and then we can determine the big M moment here. Okay, let's set this one to be the capital M1, and if you take the moment over here equal to 0, okay, you have this one for 7.5 kilonewton per meter, and this is going to be 7.5 x1. So this is going to be 7.5 x1 times x1 over 2. Okay, that is going to be 75 x1, and then you times x1 over 2. This is going to be equal to m1 equal to, it is going to be equal to 3.75 x1. Okay, let me put this one into the pink, and m1 is going to be 3.75 to the x1. Oh, since this is in the same direction, so this is going to be in the negative 3.75 times x1. And then we have another one that is going to be here. Okay, just put this one in this portion of x1, and the moment that occur here, just set this one as the m2. If you do the summation equal to 0, there is no force here, so the m2 is going to be 0. Okay, now come again over here. If you cut it over here and consider this portion, and we will have the 1.0 force here. This is m2. Use the same direction. Summation moment equal to 0. Small m2 over here also gonna be 0. Okay, and then over here we have 20 more minutes on this. You just cut again this one for the x1. So we got to have the column over here also, and this show us the x1, and the moment you compute in this direction, this one going to be small m1. Summation of the moment equal to 0. So what you have, this one is going to be m1 take moment here due to the 1.0 here is going to be x1. Okay, and then this is going to be x1 here, and this is going to be m2 here. Okay, and then you can determine this, come back into this equation. You have the delta sub c. Okay, the delta sub c equal to this one, equal to the integration of this one. You integration from b to a. Okay, you integration from this one to this one is going to be 3 meter. Okay, and then this one gonna time x1. This one is x1, and this one is going to be minus 3.75, and then x1 square, and the x1 over ei. Okay, and then we plus the integration of this x2 is going to be 0 because all of this is 0. And then you will get this one as minus 75.94 over EI. Or you get this one for 75.94 over EI. In the opposite direction of this is going to go downward. Okay, just put it, this one going to go downwards as we know about this. And then next, 1.0 is going to have F sub CC. It's going to have F sub CC here. And then it's going to be integration of M due to this. And since C sub Y and this one is the same, it's going to have M. Okay, and then it's going to be dx over EI. By doing this, it's going to be easy because we will use this one, both M. Okay, and then the F sub CC will be equal to this one. Okay, integration of 0 to 3 from this B into this one A. And then this one going to be x1 times x1 is going to be x1 squared, and then the x1 over EI, and then plus 0. This is going to be simple. It's going to be 9 over EI. Okay, and then we go further. We just go to the step 4. Okay, we solve for this one for C sub Y, and then we have C sub Y equal to this one is going to be 75.94 over EI. Okay, and this one has the same direction of this as we expect from the previous consideration here. Okay, so this one gonna be EI divided by 9. Okay, you just put this one together. The result gonna be really easy. 8.4375. This is going to be 8.4375 kilonewton. Okay, and then now you are ready to what? To analyze the structure, to determine everything. Okay, that is going to be this one. Analyze the frame. Realize the frame. Okay, and then this is what this frame is going to subjected to 7.5 kilonewton per meter, and also this subjected to 13.5 kilonewton, and then it has this one of point C that's subjected 8. This one is, let's put it into 8.44. Okay, let's put this one into 8.44 kilonewton, and then we will have this one of A sub X and this one for A sub Y, and we also going to have the moment of this one of M sub A. Okay, this one going to be M sub A. And if you do the summation of X sub X equal to 0, this A sub Y going to be 13.5 kilonewton. And then if you do summation of the moment point A, at point A, okay, just put this one to be 0. Our M sub A counterclockwise. Okay, this one have produced no moment, and 8.44 will rotate in the same direction of this one. This is going to plus 8.44 and time 3. That is going to be equal to, this one is going to be 7.5 times 3, and this one gonna be 1.5 7.5 times 3 and times 1.5. And what do you get for the result? Let me check. 7.5 times 3 times 1.5, that is 33 point. This is 33.75, and 8.44 times 3, that is 25.32. Okay, 33.75 minus 25.32, you get it for 8.43. Okay, this m sub a is 8.43 kilonewton meter. Okay, if you use this number, it's going to be 8.44 whatsoever. So this is 8.40 kilonewton meter. And then the last one, summation of f sub y equal to 0. This a sub y plus 8.44 equal to 7.5 times 3. So your a sub y is going to be 14.06 kilonewton. And then you got to separate this one into two portions. One is going to be this one for the A, B, and another one we have this one for the portion of B, C, and we have point B over here. Okay, we separate this one. We draw the shear diagram and moment diagram. We have this one for 13.5 kilonewton, and this one 13.5 kilonewton, and this one for 14.06 kilonewton, and this one for 8.40 kilonewton meter, and we also have this one for 8.44 kilonewton. Okay, and then if you balance this, you will get this one, and this one going to be 8.44. Okay, kilonewton. This is one is the upward. This one is going to be 8.44 downward. So this one is going to be 8.44 kilonewton. Okay, and then what we have is going to be this one. This one is going to be 13.5. So this one is going to be 13.5. And this one is balanced, right? Since there is no force here, the moment here will also be 0. So by doing this, we will get the shear diagram of this one to be x meter, and then what we have, this is V kilonewton. This is going to be 14.6. Okay, if you use this 10 kilonewton per 5 meter, this is going to be close to it's going to be harder. Just say 10 kilonewton per 5 meter, 20 kilonewton per 10. So this is about 7 millimeter. So this is going to be plus 14.06. Okay, and then the slope here going to be downward. dv by dx equal to minus 7.5. And for sure, this one going to cross. Okay, this one by using the scale nearly 4 something millimeter. This is minus 8.44. And then you will have this kind of shear diagram. And the length here going to be EC is going to be 14.06 divided by 7.5 by the slope. This is going to be 1.875 meter. And then what we have is going to be the moment diagram, and then we set this one up, okay, as the moment kilonewton meter, and we have this one 8.43. Okay, set 10 kilonewton meter per 10 millimeter. This is 8.43, so it's going to be 8 point something. This one minus 8.43 over here. Okay, and then what we have is the slope here of 14. Okay, this is dm by dx is going to be plus 14.06, and then over here is shear equal to 0. So dm by dx is going to be equal to shear 0. So the maximum moment supposed to be here. Moment here minus of the minus 8.43. And it's going to be equal to this area, 1/2 of 1.875 and times 14.06. Okay, if you push it into calculator, it's going to be 4.747. That is going to half of that. Okay, that is going to be 4.746 or 7. Okay, just put this one, and then the curve gonna be something like this, and the rest of this moment is 0. For sure the curve gonna be concave like this. dm by dx is going to be minus 8.44. Okay, this is going to be a moment diagram, and then we also have another diagram of this. Okay, this is 13.5. So this is the N diagram, and then this is N kilonewton and X meter. So we have 13.5. Just put this one minus 13.5. This one minus 13.5 kilonewton. This is normal force diagram. This is M diagram, and this is going to be the shear diagram. Okay, and then we come into next picture over here. Okay, and then you can see there is no shear force. So this is going to be shear diagram, this is going to be moment diagram, and this is going to be N diagram. And then you come into this, there is only N diagram here. This is in compression of 8.44. So it's going to be less than this. This is going to be minus 8.44, minus 8.44. And then just put this one to be the N kilonewton. Put this one to be M kilonewton meter. Put this one into shear kilonewton. And this is X meter, X meter, X meter. Okay, and then by doing this, we can draw the elastic curve of this structure. Okay, and then what we have, our structure is fixed here and has this one here, and under this one, okay, you have this one as the 0. This one going to concave, or this is negative, concave downward. This one is concave upward. So what we have, this one gonna concave like this, downward, and then this one gonna concave upward like this, and then there is no moment here, as I did mention. So the deformation of this one supposed to be something like this. This one is going to be the roller, and this one is going to be something like this. Okay, and this one going to keep in the right angle, and then you also can put the reinforcement onto this structure easily. Okay, this is going to be the elastic curve for this frame. I like to finish this one, and also by the same time, as you may see over here, we review our chapter 7 over here also.